All right, so this last week we've been working on searching for common ground, um, which is common factors and common multiples. We've also been working on section 5 as well, but we started with a lot of section 4 work. Learning goals: identify the factors of numbers and the common factors of two whole numbers. Learning goal: identify the multiples of numbers and the common multiples of two whole numbers. 3. Write and evaluate numeric expressions using the distributor property to model composing and decomposing the areas of rectangles. Whew, we did it. That sounds confusing there. Next, rewrite the sum of two whole numbers with a common factor as a product using the distributive property. We did that. Key terms: common factor, relatively prime, greatest common factor, multiple, commutative property of multiplication, least common multiple, LCM. So we took apart some shapes, we tried to put them back together. We're taking apart numbers, we're trying to put them back together. You've done some common factor and common multiple work in the past. You've also dealt with the commutative property of multiplication. For some reason, it was called the turnaround rule, which is silly. I digress, though. But you've had experience with a lot of this stuff before. Okay. Now our warm up, we did the factor pairs. I know together we did 42, and we did it like a T-chart, so to help us out. We also did 56, and we also did 84, and we might have even done 91. I was just showing them to you in different ways. And so to make it so we are clear on this, no 3, 4 works, 4 is 14, no 5, not 0 and 1, no 6, 7, no 7 and 8, right? 7 times 8. Yep. And then that's 8, so it's on the other side, so I know I'm good. 84. 1 and 84. 1 is always 1 with that. And then we have 2 because it's even. 2 goes with 42. 3 does work with this one because 8 plus 4 is 12, so I know the whole number is divisible by 3, and that is going to be 28. Then 4 does work. With 4, it's going to be 21. 5 is no, doesn't end in a 0 or a 5. 6 is yes, because it's 1, and then it's 24, so it's 14. 7 is a yes, tricky one, because 7 is a 1, and then it is a 2, and then 8, no, 9, no, 10, no, 11, no, and 12's on the other side, so I know I'm done. 91, 1 and 91. Not a 2 because it's not even. Not a 3 because 9 plus 1 is 10. I can't divide 10 by 3. Not a 4, not a 5, not a 0 or a 1, or a 0 or a 5. Not a 6. 7, yes. 7 is going to be 1 and 13. 8, no. 9, no. 10, no. 11, no. 12, no. 13, and it's on the other side, so I know I'm done. All right, that is your beginning page for section 4. All right, so getting started. I was thinking through how I was going to run through this. How many rectangles can you build? Understanding the area of rectangles is helpful when learning about factors. A rectangle area model is one way to represent multiplication. Your class is going to create area models for each number, 12, 15, 16, and 20. For the number assigned to you by your teacher, use the grid paper at the end of the lesson to create and cut out as many unique rectangles as possible with the area of your assigned number. Label each rectangle with its dimensions. And I modeled doing 16 and 20, and then I gave groups either 12, or I gave individuals 12, or I gave them 15 or 12. Okay, so for 12, the dimensions would have been 1 by 12, 2 by 6, and 3 by 4. For 15, you should have had 1 by 15 or 3 by 5. Then we talked about in class, and I wrote down on my sheet for 16 and 20, how do you know if you created all the possible rectangles with the given area? When you try a different dimension, it doesn't make a rectangle. Okay, and so I think we're probably looking at 16, so I did something like 5 here. And what we found out was we got to there, and then we could only make 16 by making it so it was like that, so it wasn't a rectangle. The other thing we talked about was with a calculator, we divided it by something, and then there would be a decimal. Okay. How are factors represented in your rectangles? The factors are the dimensions. And then it says list all the factors of the numbers that you were assigned. Well, for 12, the factors would be 1, 2, 3, 4, 6, and 12. For 15, the factors would have been 1, 3, 5, and 15. For 16, the factors would have been 1, 2, 4, 8, and 16. For 20, the factors would have been 1, 2, 4, 5, 10, and 20. And so those are the factors, and that's me listing the factors. Activity 4.1, using rectangles to determine common factors. For this investigation, select a partner who has created area models for a number different from the number assigned to you. Together with your partner, combine one of your rectangles and one of your partner's rectangles to make a bigger rectangle. If possible, use this method to create additional rectangles. Complete the table with the information from each larger rectangle created by you and your partner. All right, because of how I did this, I know I did 16 and 20, and so I assigned to the group for everyone else to do 12 and 15. And so 12 and 15 would go up here. It might be reversed, and that's okay. The smaller rectangle is here, and the ones that would go would be 1 by 12 for the smaller. Oh. The other one would be 1 by 15. And the dimensions of the larger rectangle would be 1 times the quantity of 12 plus 15. And then that would be the same as 1 times 12, which is 12, plus 1 times 15, which is 15. And that would have a total larger area of 1 by 17. Next, they both don't have 2 as a factor, but they both do have 3 as a factor. And so for the smaller rectangle, 1, it would be 3 times 4. For the other one, it would be 3 times 5. And then it would be 3 times 4 plus 5. And then 3 plus 4, which is 12, plus 3 plus 5, which is 15. which is going to give us a total area of 27. Maybe I'll write that 3 times 4 plus 3 times 5. Over this one, it's 1 times 12 plus 1 times 15. And so we're showing the distributive property here for these types of problems. There should be nothing that goes in this one because there's no other common factors. And then I kind of pointed out in the example I gave that we have 1 and 3 here, which is the same as the 1 and 3 here, which is the same as the 1 and 3 here. Okay, so that is the factor we're pulling out of both of those numbers, 12 and 15. And then I also pointed out that this was 12 here, and this was 12 here. And this was 4 here, and this was 4 here. Conversely, this was 15 here, this was 15 here. This was 5 here, this was 5 here. So it kind of continues on. How are the dimensions of the larger rectangle related to its total area? So here are the dimensions, okay? And so the dimensions, so the dimensions of the larger rectangle equal the area of the total area when you simplify it, when you evaluate it. Evaluate is finding one answer. And so I evaluate it, then I get to 27. Okay. Last but not least, for each larger rectangle you and your partner created, write a numeric expression that relates the dimensions of the larger rectangle to the sum of the areas of those smaller rectangles. This is fancy language. I showed you what it was for mine, but I believe I did. And so this is kind of saying use and show the distributive property for each of these. So I had this one right here, and that would be equal to 1 times 12 plus 15. Oops. Let me restart that one. Sorry. 1 times the quantity of 12 plus 15 is the same as 1 times 12 plus 1 times 15. If I solve for each side, it would be 1 times 27 equals 27. For this side, it would be 12 plus 15, and that also equals 27. That's what they're meaning. They're saying, hey, look, show how the distributive property is just like this. For the other one that we were able to make for our two numbers, we had 3 times the quantity of 4 plus 5, which is equal to 3 times 4 plus 3 times 5. And then that would be 3 times 9, which is 27. On this side, it would be 12 plus 15, which is also 27. And so I want to show the distributive property, and I'm trying to make sure I relate it back to what we did in the table here, which was showing how the common factors can of a rectangle can relate back to the distributive property as a way to show that. All right, so now consider any factors that are shared between your number and your partner's number. These are called common factors. I like how the vocabulary words are always in bold. And then how are the common factors represented in the larger rectangles that you and your partner created? And so if I think about this, the common factors were one of the dimensions in the rectangles. Okay. Next question is, how are the common factors represented in the numeric expressions that you and your partner wrote? Well, they were always in the length section. They were the dimension of length. I made it so they were first in both of them, and we were trying to copy that. And so, how are the common factors represented in the numeric expressions that you and your partner wrote? The common factors were always the length dimension, at least in the ones that I wrote or that I modeled. List the common factors of the two numbers. So for 12 and for 15, the common factors were 1 and 3. Okay. Activity 4.2, prime factorization. So we've been practicing this. I believe I showed at least one of these numbers as a factor tree. Suppose you are looking for the common factors of 56 and 42, but you do not have grid paper or scissors to create rectangles. Plus, that would get pretty old after a while. Is there another way? One way to determine common factors is to use prime factorization. Start by writing each number as a product of its prime factors. And so basically, they're talking about making a factor tree, which is right here. A factor tree is a way to organize the prime factorization of a number. Choose any factor pair to get started. So 18, they broke it down to 2 and to 9. 9, they broke it down to 3 and 3. And then 18 is equal to 2 times 3 times 3. No matter how you broke down 18, you would end up with 1, 2, and 2 3s in its prime factorization. So for 56, they did a factor tree. For 42, they did a factor tree. They got those prime factors as your final answers. Organize the prime factors into a table where only shared factors are listed in the same column. This was confusing. I didn't like how they did this. They don't want anything to go here. They're just saying that, look, both of them have 1, 2, but 56 has a 2 and another 2, and 42 doesn't have that. 42 has a 3, but 56 doesn't have a 3. But look, they both share a 7. So those blank spots, they almost wanted to like shade out as like, don't worry about this. There's nothing that should be going in there. Don't put anything in there. Okay? And so the common factors of the two numbers are the numbers that are in both rows and the product of the numbers that are in both rows. So basically both of them have a 2. So and both of them have a 7 and both of them have a 14. The one that Krishna talked about that's not listed then is that both of them always would have 1. 1 would always be shared as a common factor between any two numbers. And so the prime factorization can show us all of the common factors, except we do have to remember, because Krishna reminded us, that 1 is also one of those common factors. How do you know that? Oops. There you go. How do you know that 14 is a common factor of 56 and 42? They both have prime factors of 2 and 7. 2 times 7 equals 14. So 14 is also a common factor. Okay. Next, why is there a space between 2 and 7 at the top row of the table? So if I look at this, that's what I was talking about when I was looking at this. For 56, there's a space between 2 and 7, and that space is because 42 has a prime factor of 3 and 56 doesn't. Because 42 has a prime factor of 3 and 56 does not. Okay. Create a table to identify common factors. All right, so identify all the common factors of 54 and 84. So we have 54 here. I'll try to show that in green, and then we'll have 84 here. I'll try to show that in orange. To make it simpler, I would definitely make a factor tree. So 54 I can break down to being 9 times 6. 9 I can break down to being 3 times 3. 6 I can be breaking down to 2 times 3. 84, put that over here in the orange. 84 would be 2 and 42. And then 2 is prime. 42 would be 6 and 7. 7 is prime. 6 would be 2 and 3. Okay, so we have our prime factors. We have this, and 54 has a 2. And 84 has a 2, and then it has another 2. And then 54 has a 3 and a 3 and a 3. 84 has 1 3. And then 84 has a 7. And that should be it. And I kind of made those spaces kind of like they did. Boom, 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 boom. Make sure I have it. 2 3 3 3, 2 3 3 3, 2 2 3 7, 2 2 3 7. Okay. Of the common factors, which one is the largest? All right, so I need to figure out the factors, and I think I'm supposed to do that in A, and that's okay. So we'll start with Krishna saying 1 is a common factor because it's always going to be a common factor of any 2 numbers or any numbers that are put together. Then they both have a 2. 1, 2, so 2 works. 3, they both have a 3, so 3 works. 4, this has 2 2s, this one does not have 2 2s, so that does not work. 5, there's no 5 in either list. 6, 2 times 3, 2 times 3, 6 would be on the list. 7, this one has a 7, this one does not have a 7. 8 would be 2 times 2 times 2, no 2 times 2 times 2. 9, 3 times 3 would be up here but not here. 10 would be 2 times 5, nope. 11 would be 11, not on there. 12 would be 2 times 2 times 3, here but not here. All right, and I think those are our common factors right there. They both have a 2, they both have a 3, they both have a 2 and a 3, and then you have to have 1. And so if I think about this, the greatest one, the GCF, is going to be 6. And we can kind of see it with the prime factorization. Okay? The greatest common factor, GCF, is the largest factor, I should say of 2 or more numbers. Oh, sorry, never mind. Is the largest factor 2 or more numbers have in common. Okay? We get down to another tricky thing, 56 and 42. Rewrite each numeric expression using the distributive property and the GCF. It's a big jump. So if I'm just using the distributive property, I could pull 1 out from both of these, and I would have 1 times 56 plus 42. And that's the distributive property. Second, I could have 2 times 28 plus 21. And also could do 7. So 7 would be 8 plus 6. And then I could also do 14. And 14 would be would be 4 plus 3. And the greatest of those would be pulling out the 14. Then for this example right here, I could do 1 because that's one of the common factors. So it would be 54 plus 84. It would be 2, which would be 27 plus 42. It could be 3, which would be 18 plus 2, 8. Or it could be 6, which would be 9 plus 14. Let's see here. Yep, that is correct. And then the largest one, the greatest common factor, would be 6. Okay? Real quick before I'm done with this page, 2 things. Notice how this problem right here relates to this problem right here. And then if I was paying attention, this one relates to the worked example. And I want to be paying attention to those samples because a lot of times they'll ask me questions about what I've done before. I've got to connect my work to what I was doing before. I definitely have to pay attention to when they give me an example. Weird definition over here. I like this definition because it was something that I learned when I first started doing this math. 2 numbers that do not have any common factors other than 1 are called relatively prime. So if I was to take like 9 and 8, factors of 8 are 1, 2, 4, and 8. Factors of 9 are 1, 3, and 9. The only common factor is 1. They only both have a 1, so these 2 numbers are relatively prime. Okay? Relatively is compared to one another, and so those 2 are relatively prime. Activity 4.3, common multiples. Rectangular arrays can also be used to determine multiples and common multiples. A multiple is the product of a given whole number and another whole number. Consider the area model for 6 times 8 equals 48. One way to think about the area model is to analyze the collection of columns. So columns are going this way. As you look at how the area model builds from left to right, the addition of each new column creates a multiple of 6. So column 1 alone is 6 times 1, or 6, which represents the first multiple of 6, which is 6. By adding column 2, the rectangle is now 6 times 2, which represents the second multiple of 6, which is 12. The whole rectangle represents 6 times 8, or 48. Number 1, list the first 8 multiples of 6 by labeling each column of the area model. 6, 12, 18, 24, 30, 36, 42, 48. The commutative property of multiplication states that for any numbers a and b, the product a times b is equal to the product b times a. So basically 6 times 8 is the same thing as 8 times 6, which I believe they used to call the turnaround rule. Next, think about the area model as a collection of 6 rows. The first row alone creates an 8 times 1 rectangle, which represents the first multiple of 8, which is 8. Including all rows of the 8 by 8 times 6 rectangle represents the sixth multiple of 8, which is 48. So we have 8, 16, 24, 32, 40, and 48. And so if we had that, it would be up there, but the first 8 multiples of 6 would be 6, 6 times 2, 6 times 3, 6 times 4, 6 times 5, 6 times 6, 6 times 7, and 6 times 8. And down here, we would have the first 6 multiples of 8, 8 times 1, 8 times 2, 8 times 3, 8 times 4, 8 times 5, and 8 times 6. Okay. All right. So while 48 is a multiple shared by both 6 and 8, it is not the least common multiple, or LCM. The LCM is the smallest multiple, other than 0, that 2 or more numbers have in common. Analyze the multiples of 6 and 8 that you labeled on the area model. Identify the least common multiple of 6 and 8. So in the area model, we had 6 was 6, 12, 18, 24, 30, 36, 42, and 48. At the same time, 8 was 8, 16, 24, 32, 40, and 48. And we got all of those. You can see that 48 was a common multiple, and that's the same as 6 times 8. But there's one that's less than that is the least common multiple, and that one would be 8. Okay? As demonstrated by the rectangular array, for any two whole numbers, a and b, a common multiple is a times b. However, this number may not be the least common multiple of a and b. Okay? In English, this is saying if I multiply two numbers together, that will be a common multiple. However, sometimes there'll be a least common multiple that is less than the product of the two numbers. And we've been trying to show that by showing you factor trees. And for factor trees of 6 and for 8, we see that 6 is 2 times 3, and we see that 8 is 2 times 2 times 2. And when we make our least common multiple, our LCM, it has to have all of 6 in it, and it does have to have all of 3 in it. So first I have to write down a 2. So I put a 2 in there, and that 2 would count for the first 2 there. And so it's a double counting. So this 2 is also that first 2 there. And then I still need to get those two 2's in. Now I'll have all 3 2's for all of 8, and then to get all of 6 in, I also need to have a 3. And when I multiply that together, I do in fact get 24. Because I double counted those 2's, well, it's not the same as the product. It's half as much as the product, because I would take this times 2 to get to that 48. Okay? So that's sort of why. But the product of any two numbers will be a common multiple. However, sometimes when they share prime numbers, the least common multiple will be less than the product. All right, determine the least common multiple of 6 and 9. List the first 9 multiples of 6. All right, 6, 12, 18, 24, 30, 46, 42, 48, 54. All right, and then list the first 6 multiples of 9, 9, 18, 27, 36, 45, 54. Okay, and so these are my multiples of 9. These are the multiples of 6. What is the least common multiple of 6 and 9? The first one that is the same in both is, in fact, going to be 36. So the LCM is going to be 36. Determine the least common multiple of 7 and 8. Okay. The least common multiple of 7 and 8, LCM, is going to be 56. I know this. Well, it deals with number 6. But if I was to list the multiples of 7, 7, 14, 21, and I would want to go back and forth. If I really don't know a common multiple, I would want to go back and forth, and I'd probably want to start with the bigger number and then kind of go from there, if at all possible. 32, 40, 48, 35, 42, 49, 56, 48, 56. Voila. We have 56. Okay. Last question here. Using prime factorization, how can you determine whether the least common multiple of two numbers is the product of the two numbers or is less than the product of the two numbers? All right. So for number 5, the least common multiple was the product of the two numbers. If I do prime factorization, 7 is prime, so that is the prime factorization for 7. For 8, the prime factorization for 8, which we've done before, is 2 times 2 times 2. Okay? And so this one, it is the product because it's off the page, isn't it? Sorry. It is the product because the two numbers, or the numbers, if there's 3, the numbers don't share any prime in their prime factorization. Again, if we look at 6 and 8, 6 and 8 share 2 as one of their common primes, and so then it's less than the product. All right? And so I would almost want to say 6 and 8 is less than the product because they do share a common prime factor in their prime factorization. And that is a super tricky problem for 6th graders to get. And so we've been practicing and we've been showing how we can get an LCM by listing the multiples. And we've also been showing how we can use the prime factorization. And I've been trying to give you examples where they do share prime numbers in their prime factorization. And I've been trying to give a couple of examples where they don't share prime numbers in their prime factorization. All right, now we got the talk, bringing it back around. answer each question to show how to use the distributive property to decompose numbers. All right, so consider the sum 36 plus 24. Okay, express the sum 36 plus 24 as many ways as possible as the product of A times the quantity of B plus C. Okay, so when I'm using the distributive property, I'm kind of coming up with a common factor. So I'm going to answer B first. I use or pull out or factor out a common factor when using the distributive property. I know I'm done if I used all the common factors. Okay, so if I take a look at this, my common factors between 24 and 36 are 1, 2, 3, 4, 6, and then 12. Okay, so when I write this, I can write this as 1, 2, 3, 4, 6, and 12. Okay, notice how I use blue with both of those so you can see how that is. Now I just have to put inside of this the factor pairs that go with 1. So for 36, it's 36. For 24, it's 24. When I pull out 2, the factor pair for 36 is 18. For 24, it's 12. When I pull out 3, the factor pair for 36 is 12. The factor pair for 24 is 8. For 4, the factor pair is 9 for 36, and it's 6 for 24. For 6, it's 6 for 36, and it's 4 for 24. And for 12, the factor pair is 3 for 36, and the factor pair is 2 for 24. Mrs. Cheku was pointing out that I kind of know I'm done here because I got to 2 and I got to 3 for what's inside of there, and those are both prime numbers. And so I can't pull out anything else besides that unless both of them are divisible by that prime. Okay? So that is how I do the top part. Number 2 is related to number 1. Suppose you have a composite figure composed of a rectangle and another parallelogram with a shared side. Okay, so if I look at this, we have B right here, and we have this would be the same length as B because it's a parallelogram, it's a rectangle. Okay, the area of the rectangle is 72. So I know this has to be 72 centimeters squared no matter what. Then I know the parallelogram has to be 84 centimeters squared no matter what. Okay. Now I am using I listed all the factors using a T-chart or table. And now what I want to do is I want to think about all of the possibilities for B, because B is the base for this rectangle, and whatever B is, it has to be able to be used for the base for this parallelogram. Okay, So B can only be the common factors of 72 and 84. And so I could almost think of making a table here for what B would be. Sorry. And then based on that, what A would be. And then based on that, what H would be. Okay? So the first thing that B could be is 1, because they both share 1, and 1 would be in both of them. Now for the rectangle, it would be 1 times 72 to get that area. For the parallelogram, it would be 1 times 84 to get that area. Next, they both share a common factor of 2. So B could be 2. If B is 2, then A would have to be 36 to equal an area of 72. If B is 2, H would have to be 42, so it would have an area of 84. Next, they both have 3 as a common factor. So 3 could be B. If 3 is B, then A would have to be 24, so it equals 72. If B is 3, H would have to be 28, so that area is 84. They both have a common factor of 4, so B could be 4. If it's 4, it would be 4 times 18 for A. If this is 4, it would be 4 times 21 for H. They both have 6 as a common factor, so 6 has to be in my table. If this is 6, A has to be 12. If this is 6, H has to be 14. They both don't have 8. They both don't have 9. They both do have 12. So if B is 12, then A would have to be 6. And if B is 12, then H would have to be 7. I'm looking to see if any of these are the same, and this one's not quite the same, actually. Okay, we're almost done. Then both don't have 14, both don't have 18, both don't have 21, both don't have 24, both don't have 28, both don't have 42. All right, and so those are the possibilities, and so I used common factors to see what their factor pair would be, to see what the dimensions of this composite shape could possibly be, where this has an area of 72 and this has an area of 84. Very tricky question. Hopefully we understand it a little better now from watching that. And if you got it, way to go.